I have a couple of gas law problems to go over with you. There's not too many equations in this chapter, and one of them that will actually help us do several different types of problems is P1 V1 over T1 equals P2 V2 over T2. So for this problem we have here 22.5 liters of nitrogen gas at 0.984 atmospheres is compressed to 725 millimeters of mercury at constant temperature. What is the new volume? So if we start labeling the variables we have, this 22.5, that is V1, 0.984 atmospheres is P1. It gives us P2 here as 725 millimeters of mercury, and it asks for the new volume. So I'll write V2 equals a question mark. Now, one of the key things here is it says at constant temperature. So what that means is with this overall equation, we can basically take out the temperature and we're left with the equation we want, which is P1 V1 equals P2 V2. Now that goes along with Boyle's law. So I'm going to rewrite it down here. P1 V1 equals P2 V2. When I look at this, one of the things that jumps out at me is that the pressures do not match. One is in atmospheres and one is in millimeters of mercury. Now, it doesn't matter if you convert them both to be atmospheres or both to be millimeters of mercury. As long as they're the same units, that's really all that matters. So what I ended up doing, and I'll actually show you both ways, you should get the same answer either way. So for the first one, I'm going to convert the 0.984 atmospheres to millimeters of mercury. Forgot to add the units in. So if you start off with atmospheres, atmospheres goes on the bottom. You're looking for millimeters of mercury, so that goes up top. And you just use standard pressures as the conversion factor, because remember, a conversion factor, you have to have an equality there. So 1 atmosphere is the same thing as 760 millimeters of mercury. You just get different numbers because the units are different. So when you do the math for that, you get 747.84 millimeters of mercury. And since this is 3 significant digits, is 0.984, we round our answer off to 3 significant digits, and you get 748 millimeters of mercury. So now that is what I'm going to use as P1. So when we do this, I could plug those numbers in. P1 I'm giving as 748 millimeters of mercury. V1 is 22.5 liters. P2 is 725 millimeters of mercury. And V2 is what we are solving for. Now when you do this, this is why you needed the units to be the same. What we end up doing is multiplying these two variables on the left and then dividing by that 725 because we want V2 by itself. All right, so what we have to do is divide by 725 millimeters of mercury. What you do to one side, you do to the other. Right, so those millimeters of mercury will end up canceling out. What you should get as an answer when you do this is V2 equals 23.2 liters. And again, everything in here is 3 significant digits. So I round my answer off to 3 significant digits. Now, if we ended up doing the other conversion, so I'm going to erase some of this stuff. I'll just erase it all like that. So let's say I took the 725 millimeters of mercury, which we had listed as P2. So let's say I took that and converted that to atmospheres. Again, using an equality for the conversion factor, 760 millimeters of mercury is 1 atmospheres. Since I start off with millimeters of mercury, I need millimeters of mercury on the bottom. So when I do that conversion, that becomes 0.954 atmospheres, rounded off to be 3 significant digits. So this is what I'll use for P2. Now you obviously don't have to do this problem twice. I'm just showing you that no matter what, you will end up with the same answer. So P1 was 0.984 atmospheres. V1 is 22.5 liters. P2 is what I just did the conversion for, 0.954 atmospheres, and I'm solving for V2 using the same same method as the last one. Multiply 0.984 times 22.5, divide by the 0.954. You should still get the same answer for V2, 23.2 liters, rounded off to 3 significant digits. All right, so that was a Boyle's Law problem. I'm going to erase this and scroll down and do another problem. All right, now it's giving us different variables here. A container containing 5,000 milliliters of a gas is collected at negative 173 degrees Celsius and then allowed to expand to 20 liters, 20.0 liters. What must the new temperature be in degrees Celsius in order to maintain the same pressure? Remember, pressure has to do with collisions. Anytime particles are colliding with the walls of the container, you get pressures. What this is saying is the number of collisions are staying the same. Now, if we start off with that same overall equation, P1 V1 over T1 equals P2 V2 over T2, what's going on is pressure is staying the same. So basically pressure is taking out of this equation. And what you end up with is a Charles Law problem. V1 over T1 equals V2 over T2. Now you have to look at the units again. What happens is one of the volumes is in milliliters and the other one's in liters. And again, it doesn't matter which one you change. You can have them both as milliliters or both as liters, and it doesn't matter, but they have to be the same units. The other thing, and this is something that people forget a lot, is the temperature has to be in Kelvin. Kelvin is said to be like the absolute scale. So whenever you do a gas law problem, you have to do the problem in Kelvin. Now, even though I give you the temperature in degrees Celsius and ask for the answer in degrees Celsius, you still use Kelvin in this equation. So you convert to Kelvin, do the math, and then convert it back to Celsius. So what we do here is, let's label everything. So 5,000 milliliters, that was V1. The 173 degree, or negative 173 degrees Celsius is T1. It's allowed to expand to 20 milliliters, that's V2, and it's asking for temperature 2. That is what we have to solve for. So we can start plugging these numbers in. Now for me, I just made both of the numbers into liters. You can make them both milliliters if you want, but I'm going with liters. So I convert V1 into 5.000 liters, and I have all those zeros in there just to match the significant digits in the problem. T1 is negative 173 degrees Celsius. We have to convert that to Kelvin, so it becomes 100 Kelvin. V2 is 20.0 liters, and T2 is what we're solving for. Now, there's a little bit of variation in how you can solve this problem. What I usually do is I would usually figure out this left-hand part here. So you do 5 on your calculator, basically 5 divided by 100, which would give you 0.0500 to match the significant digits. And the units are liters over Kelvin. And then that equals 20.0 liters over T2. Now, if you want to solve for the denominator here, basically what happens is these two things end up switching places. And the reason why that is the case is because you have to multiply both sides by T2. And now you want to get rid of this 0.0500, so now you divide both sides by 0.5 or 0.0500, and what you end up getting there is the T2, and that number ends up switching places. So let me clean this up a little bit. So what you should end up getting is T2 equals 20.0 liters divided by 0.0500 liters over Kelvin. The liters will end up canceling out, and what you'll get is your answer in Kelvin, and it equals 400 Kelvin. But I asked for the answer in Celsius. Now what happens here, and I'm going to jump back a little bit. For this number to go from Celsius to Kelvin, I added 273. And when you add, you go by the least number of decimal places. Since this is a whole number, I wrote my answer as a whole number in Kelvin. Now down here, I have 400 Kelvin. And what I did is I went by the least number of significant digits, which I just realized I forgot to write some of them in there, although it's not going to change anything. I should have an extra 0 there. So what happens here is the 20.0 is 3 significant digits. So I rounded my answer off to 3 significant digits because that is the smaller of the two. And just to make the colors match, now what I have to do is subtract out 273 to get it to Celsius. Now since I'm subtracting and 400 is a whole number, I need my answer as a whole number. It becomes 127 degrees Celsius. All right, now another way people tend to do this, and I'll just do a little bit of erasing here. And again, you obviously don't have to do this problem 2 different ways. I'm just showing you the 2 ways I tend to see it done. You could just do cross multiplication here. So what you would end up getting is 5.000 liters times T2 equals the 100 Kelvin times 20 liters, which gives you 2,000 liters times Kelvin. Now, if you want to match significant digits, and since they're both 3 significant digits, you could write this as scientific notation if you wanted. And now what you do is divide both sides by 5. So T2 equals 2,000 divided by 5, which gives you the answer of 400. And since this is 3 significant digits, I round my answer off to 3 significant digits. Subtract out the 273, and that gives me that 127 degrees Celsius again. All right, so that is a Boyle's Law problem and a Charles' Law.